Okay, good afternoon, everyone. My name is Mike Zadilla. It's my pleasure to welcome everyone to the CST 3-minute thesis competition for the spring of 2022. I'm very excited to get this event kicked off. It was a lot of fun last year. And we have some great presenters today who are going to share with us short overviews of the science that they have performed during their study. So here are the rules for the competition. Every presentation is limited to 3 minutes. Each presenter will have a single PowerPoint slide that they can use to illustrate the points that they want to make. There are no transitions or animations or movement of any kind in the slides. No additional electronic media, no sound, no video files, only the single PowerPoint slide and the voice of the presenter. No additional props, no costumes, no musical instruments or equipment. It's no show and tell other than what's on the slide. And all the presentations are to be spoken word, no poems, raps, or songs. I want to recognize and thank our judges who volunteered to help us determine the outcome of the competition. We have Art Dawson, the chairman of the board of directors at New York Presbyterian Queens, and a member of the CST Board of Visitors. We have Churam Chowdhury, who's a scientific director and research fellow at Safety Pharmacology at GSK. And we have R.J. Lazik, the vice president of commercial and customer operations for Becton Dickinson and Company. So thank you very much to the judges for your time and your service for this exciting competition. And with that, we are ready to start the competition. So our first presenter is Hannah Kim, and the title of Hannah's talk is it changing or not changing? That is the question. Property-informed models of evolution. And with that, Hannah, the floor is yours.
Thank you, Dr. Zadilla. Okay, I will start my talk. For the past 2 years, the world has undergone the global pandemic of COVID-19 caused by a virus called SARS-CoV-2. This family of virus is characterized by the crown-like structure surfaces. We know from the experience that diagnostic tests such as nasal swabbing is used to determine whether we're infected or not. Researchers can use the same swab samples to understand how the virus evolves over time. Thanks to the efforts of the global community, there are about 10 million samples available to researchers online. Using this unprecedented amount of data, major changes in the virus can be tracked. As a result, we know when variants like Delta and Omicron rise. Understanding the changes in genomic sequences is important because changes in RNA lead to changes in protein, and changes in protein structure leads to changes in protein function. Now, how else can we extract information about changes that a virus is going through? What if we can tell that a functionally important viral protein is meaningfully changing? What if we can tell why? If we can tell which properties are responsible, wouldn't we be able to use that information to find drug targets? We may even be able to foresee what other changes that the virus will go through. This is where my project, Property-Informed Models of Evolution, PRIME, comes in. PRIME builds on top of the cutting-edge model of evolution. My model can identify evolutionarily significant properties that can explain why the virus changed. To understand the significance of the method, let's look at a SARS-CoV-2 example. The virus enters the lung cell by binding to its receptor. To find ways to block the virus, we want to know how much the viral protein can change. If we know which properties are evolutionarily significant, we can understand which changes will break or not break SARS-CoV-2, even for the variants that we have not seen yet. Note that this method itself is not inherently specific to SARS-CoV-2 or viruses. SARS-CoV-2 example just outlines what could have been done earlier. PRIME's potential is in monitoring changes in pathogens in animal reservoirs worldwide. perhaps with my method, we will be able to stop the spread of the future infectious diseases beforehand. Thank you.
Okay, great, Hannah. Thanks very much. So these samples that are collected, 10 million samples, are these I guess must be collected at hospitals or at clinics?
Yes, that's correct.
Yeah, I was curious because I've taken ones at home, but I guess those just go in the trash can.
Yeah, I think these kind of samples generally require patient consents basically before it gets used in like those kind of research. Yeah.
And so now I have a question about tracking the cause of the evolution. You say that you can identify, when you say why the virus mutates, that means you can identify what selective pressure caused it to mutate based on what part of the genome is changed?
Well, basically so the selective pressure part can be done without my method. It is already, that's the cutting edge part of the model of evolution that exists. But what my model can add is that, you know, we want to know like what limits, like what kind of properties, like is it volume, is it charge, hydrophobicity, like what kind of constraints actually limit like usually like we don't know like what is, like we may sort of know based on evolutionary history, but we want to know why it changes, and that's what my method does. That's
see.
what
So this sounds like it's a more physical basis than a phenomenological basis for what's changing. And I guess that suggests that do we know the genome pretty well to know what each protein is doing in the virus, or do we not need that information?
Well, we should have a better idea. It's better to have a good idea about what the function is. Like this SARS-CoV-2 pandemic was a very special kind of occasion in that new information was just popping in like every day. Right. But I do admit that that may not be the case with all different kind of pathogens. So.
Okay, well, thank you very much. Thanks for a lovely presentation.
Thank you.
So we'll continue with our next presentation from Connor Kollner. And the title of Connor's talk is Self-Assembled Structurally and Functionally Mimetic Metalloclusters Inspired by the Oxygen Evolving Complex of Photosystem II. Connor, the floor is yours.
Thank you. So the progression and evolution of global civilizations has been accompanied by an ever-increasing demand for energy. The consequence of this is environmental instability and fluxes in biogeochemical cycles. So to correct for this, we need more advances in sustainable energy. And an attractive solution would be a solar hydrogen economy. This utilizes abundant resources such as sunlight and water to produce energy for our needs. A prerequisite for affordable and efficient systems, however, is catalysts, particularly catalysts from sustainable sources. So as a synthetic bioinorganic chemist, I take inspiration from nature. So in the top left here, I have an example of nature's biological machinery that is responsible for such chemistry. And a key feature of nature is photosynthesis, which takes in sunlight and water, as I mentioned, and turns it into energy for the plants. And the active site shown next to this protein is the oxygen evolving complex. So my work has been focused on making synthetic model complexes of this active site. In particular, model complexes that mimic the structure and function of this active site. So I have here a wide variety of complexes that are heterometallic in nature with various ratios of calcium incorporated in them. So I have this wide array of structural analogs, and it's important to probe their electrochemical properties. So we do this through cyclic voltammetry and gas chromatography. In cyclic voltammetry, we measure the current as we sweep the potential. And then in concert with that, we can measure the gaseous byproducts from the headspace of the electrochemical cell. What we see here is actually not water oxidation, but carbon dioxide production. This is a consequence of the solvent decomposing. However, it highlights two key features of these synthetic analogs, and that is one, that calcium is necessary for activity, and two, you get increasing activity with increasing similarity to nature's active site, which is very interesting. So as a consequence of my research, I was able to further extend this to a variety of other systems using different metals, mainly cobalt and iron, as well as calcium. So in the lower right here, I have shown the full array of compounds that I was able to discover through similar synthetic techniques that I've explored in our research. And I will close with that.
Okay, thank you, Connor. Very nice talk. So you're building these molecules that are meant to look like nature and have the same composition, but then you tried some other complexes with different elements. How important is it to get the composition exactly like nature? And is there an advantage to changing nature's design and trying other metals?
So nature grabs what's available in its environment. So at least at the onset of the research, it was important to try to mimic those species, be it manganese and calcium. However, in a synthetic system, you don't have this biological machinery in the form of a protein to assist in rearrangements and activity and so on. So it might be, more important for a synthetic system to feature different metals that would result in a cluster that doesn't need the biological machinery. So it's important to investigate a wide range, or I guess a wide library of species, in order to see what the most the most active synthetic species would be.
Okay, and one more question. So, you're going to all this effort to mimic nature's catalyst. Is it possible we could just use the natural protein and develop technology that just uses what nature gives us to do water splitting?
So I believe there are such farms, if you will, that use microorganisms, photosynthetic microorganisms. However, and I do admit I'm not well read on the cost of implementing these at a large scale, but I think for more residential commercial use, it might be more interesting to have synthetic materials.
Okay, thank you very much, Connor. Nice work. All right, we're going to move on to our next talk from Jay Padil. And the title of Jay's talk is Magnetism from Non-Magnetic Materials Interface for Future Generation Electronic Devices. Jay, the floor is yours.
Thanks, Michael, for the introduction. Hello, I am Jay Padil from Physics Department. So I would like to first start with keywords that might be a little bit complicated for the general audience, like magnetic and non-magnetic materials are those which are attracted or not attracted by the magnet. And also the interface, which I will be using frequently here, is the junction between the two materials, which you can see in the middle panel, top panel of the middle slide. And electronic devices are, of course, familiar. That they are the devices that we usually in our daily life. And in the motivation part of left corner, you can see that in the past, they are of the room size. And now the technology has developed significantly to miniaturize the devices and also perform them faster. But this race is not over yet. And we want to increase the performance of these devices much faster with greater storage capacity. And we want to decrease the size even smaller for the future generation demanding technological advancement. And here is the materials in the middle panel. You can see I will be using metallic LNO and insulating LNO. That is the key difference between the two samples. And the interesting part is that when we reduce the thickness of this lanthanum nickelate, it becomes insulator. So insulator does not conduct heat and electricity, but metal does. So that is the difference between metal and insulator. And depending on the metal or insulator, at the interface, there will be different behavior of magnetism. So that is my interest of the topics. And we will use the X-ray source to probe this kind of behavior. Similar to when we go to the hospital, they do the X-ray and examine our body. We go to the different lab, national and international facilities, and do the X-ray of our sample, collect the data, and analyze them. In the rightmost panel, you can see the result of my experiment. And this is the intensity of emitted electron because of the X-ray get inside into the material. And this is the intensity. And between these two peaks, the difference of the splitting is very, very different between sample 1 and sample 2. You see the sample having metallic lanthanum nickelate has the different behavior at the interface and bulk, but in the insulating sample that is same. So that is the very, very interesting, and that might justify the different magnetism behavior at the interface having insulating and metallic LNO. So it might be useful to enhance the study for the future generation spontaneous devices for our new technology. And this dimension of these materials are very, very thin, nanometer scale, which is even 1,000 times smaller than our human hair. Thank you so much.
Okay, thank you, Jay. So in this assembly, which part is the magnetic part?
Oh, yeah, sorry, I forgot to tell that. The magnetic part is towards the calcium manganate oxide. So that's towards the yellow part at the interface.
Okay.
So that's not from the lanthanum, the red part, the lanthanum.
Right. Okay. And in your these are photoelectron spectra?
Yes.
Oh, I see. We're looking at the manganese. And so you see, you have this different spectra where you have peaks and valleys. And
yes.
what do those tell us? What does a positive peak tell us? And what does a negative peak tell us about those elements?
Oh, that's really, you mean in the difference?
Yeah.
Oh, okay. So that's really a good point. So actually, we are just looking these positive left values and positive right values. That tells that there is a difference in the peak intensity between the interface and bulk. That's why they are separate. One goes towards left, another goes towards right. That's what it's causing the difference. And this on the middle, that's negative. It's just a difference in the intensity. And that does not signify anything, but it's, I think, a mathematical quantity. But having the two peaks on the left and right tells that there is a difference in the peak intensity between interface and bulk.
I see. So it has more to do with what's moving, with the peaks moving left and right.
Like whether it's moving left, right, or not. If it was completely overlapped, then there will be the flat straight line.
Okay. And is it the interface with the neighboring material that causes the difference in properties, or is it just the fact that it's no longer the bulk material that causes it to behave differently?
Oh, yeah, that's a really good question. So it's actually the interface that causing this is the magnetic and this interfacial property. You see here lanthanum nickelate in the thicker length that is metallic. It gives the charge to this yellow part, calcium manganate, and that gives us this difference in the interface for the metallic part. But however, in the insulator, it does not want to give the electron to the calcium manganate part. That's why there is no difference in the interface and bulk. So that's the key thing. It's actually the another.
Okay. Yeah. Thank you, Jay. Very nice talk and good answers. Thank you very much. All right. So now we're moving on to our final speaker, Ashley Kirker. And the title of Ashley's talk is Isotopes and Modeling to Demystify Urban Runoff. Ashley, you have the floor.
Thank you. So every single one of us lives in a watershed, and living in a watershed comes with responsibilities. But in urban areas where concrete and shingles and asphalt dominate the landscape, watershed management gets complicated. We use green infrastructure to try and slow down the problems caused by urbanization, like flooding, polluted water, and impaired streams. Even though 83% of the US population lives in an urban area like Philadelphia, too often urban watersheds are treated like a damaged version of a natural forested watershed, or as a black box where floods come out when rain goes in. So thinking of urban watersheds as analogous to forested ones is like hearing that it's 75 and sunny in LA and going sunbathing in Manayunk during Hurricane Ida. Our watersheds deserve better, and that's where geochemistry and modeling come in. I measured the natural isotopes in nitrate from this stormwater basin, which captures runoff from this larger watershed. And because atmospheric sources of nitrate, like precipitation and car exhaust, have heavier oxygen than sources from the terrestrial environment, like soils and lawns, I can determine for each point in time what % of nitrate comes from atmospheric sources and what comes from terrestrial ones. I found that at the beginning of storms, atmospheric sources make up around half of total nitrate, and at the end, terrestrial sources are dominant. What this suggests to me is that even though resource managers plan for this storm basin to capture runoff from the entire watershed, that's not always happening. I wanted to find out more about how these changing sources behave in different types of storms, so I turned to runoff modeling. I use a gridded surface model called GSSHA, and it's usually used for big watersheds and for pollutant tracing, so using it to track the path of a single drop of water in a small watershed to a storm basin is a little unusual. But it revealed that there are portions of this watershed where rainfall infiltrates into the soil before it ever gets a chance to reach the outlet, and I call these dead zones. And there are parts of the watershed where runoff is generated with even the tiniest hint of rain, high runoff zones. Dead zones are usually in areas that are flat and can infiltrate water, like this athletic field on the right, and high runoff zones correspond to areas with steep slopes and at least some impervious surfaces. In urban hydrology, we usually assume that to protect water bodies and reduce runoff, impervious surfaces should be separated as much as possible from streams and storm basins. So it's really interesting that when I used the model to move the impervious area closer to the basin inlet and the athletic field further away, like you can see in the land use to your right, I did not see an increase in runoff. And my research shows that instead of relying on assumptions, in urban watershed management, we need to actually determine the areas that generate the most runoff and prioritize them for green infrastructure. Thank you.
All right, thank you very much for your presentation, Ashley. So I suppose what I'm wondering is, so the first thing I want to ask about is you were tracking nitrates in this work?
Yeah, nitrate isotopes in stormwater.
Oh, so you're using ice, and the isotope is how you tell whether it came from the atmosphere or the soil.
Isotopes of nitrogen and oxygen.
Okay.
Within the nitrate.
So is the nitrogen that is in the atmosphere coming from a different source, a pollution source than the nitrates that's in the soil? Do we know where they come from?
So soil nitrogen can be a combination of nitrogen from fertilizer and nitrogen from like natural soil organic matter, sometimes like other sources, but those are the two big ones. And then ever since humans started sort of messing with the nitrogen cycle, most atmospheric nitrate is actually human created. So our cars produce nitrate with exhaust. We get it from like burning matter in factories or different fuel generation, and then it'll fall back down as either wet or dry deposition.
Okay. So it sounds like in your work, you developed this computer model to predict how, okay. And in this model, is this a canned program that one is okay? So
yeah, the U.S. Army Corps engineers.
I see. So you were able to use this to try to design a layout for where to put things in order to prevent runoff. That's a capability we have? Is that something that urban planners always use, or are they required to use it by law, or is this something that you and people in your community are still trying to encourage people to do?
I think it's a little bit closer to the latter, and a lot of times it's because we're sort of retrofitting a lot of things. We're not starting from scratch, but the idea that like having a bunch of pavement close to the basin inlet isn't necessarily a big red flag for water health is, I think, kind of the most counterintuitive part. So it's sort of this combination of like, yes, your land use is important, but the topography and the steepness is also really crucial in runoff generation.
Right. So are there many things that one can do if the land is old and the town is old, like Philly, and it's too late to change the design? What are there things one can do to using what you find from your simulations?
I think it could be really useful in assessing how successful your basin is. So if we think our basin is supposed to be capturing all this water and it's not, maybe we should readjust our expectations for what comes in and how we compare that to what's coming out. So maybe more in terms of like reallocating funding and judging our basins.
Okay. Well, thank you very much.
Thank you.
Thanks, Ashley, and thanks to all the presenters for some lovely talks. At this point, our judges are going to convene and they're going to begin making their assessments. And I want to share with all of you how the judges will make their decisions. So these are the following judging criteria. Comprehension, in other words, how well did they understand the science that was being explained, the content, so the richness and detail of the science itself, the engagement of the speaker in connecting with the audience, and the communication skills, and that could include communication of the science itself and clarity of speech, as well as the interactions with me, the MC, in the Q&A. So the judges will be working on their assessments of our 5 speakers, but we also invite all of you, the viewers, to vote on your favorite of our 3-minute thesis competitors' presentations. And so I believe Megan, who's managing this, is going to share with you a poll, which you can now see. So go ahead and make your choice and submit for your favorite talk. While the judges are making their choices, I would just like to engage our presenters a bit more and just ask you some more questions about your research experiences. And so the first thing that I want to ask each of you to comment on is, so you're all presumably fairly new to, well, you're all new to doing graduate research. Perhaps you did research as undergraduates, but what I'm interested to know is, as you started this research project, there's probably been some surprises. So what was the most delightful and pleasant surprise you experienced in your graduate work? And what was the most frustrating or annoying surprise, thing that you didn't expect that was going to happen? And I think what we'll do is we'll go in reverse order as the presenters went. So Ashley, why don't you share with us your thoughts on that? And remember to unmute yourself. There we go.
That'll help. So my most exciting sort of surprise, I think I got the chance to do a lot of like work with undergrads and bringing them out to my field site. So it was really cool to make sort of discoveries about the way that the nitrogen isotopes were changing and have those be shareable. And I think honestly, just like seeing a correlation and seeing a line and being like, oh my gosh, it's linear. Like, this is very exciting. We have a mixing relationship. Most disappointing, I really, really wanted one of my tracers, in addition to nitrate isotopes, to be like single cell diatomaceous algae. And they're just so hard to find. And it was very sad to not be able to find them throughout the soil. So.
Okay, thank you. Yeah, we go out on a limb when we do research and we expect things to work. And when they do, it is very satisfying and a bit of a relief. Okay, Jay, would you care to share your thoughts on the subject?
Sure, thank you. So I am an international student. So I travel all the way from Nepal to here, 8,000 miles to do the research in my graduate school. And I was so excited because I have never been to out of my country. And I joined here Temple in 2017 and joined the research group, another research group, before joining this research group. And I actually, at that time, I decided to do some kind of thin film oxide materials research, which I presented today. And the most pleasant thing is that when we usually go to the synchrotron live and collect the data here. And it was long waiting time. Like, it has to go with the proposal and it has to be accepted. And it has a long waiting time. Sometimes we go 2-3 times a year. So we are so excited for that. And we usually go to new places. That is also exciting, like in the Europe. So that is excitement part. And also we have prepared so much for the beamline. That is also exciting part. And the frustrating part comes followed by this experiment, is that when we collect the data, long waited collected data, and in beamline we didn't have that much time to analyze there. And we collect the data in our pocket and come here and open it. And when we look, and sometimes we just collect garbage. That might be possible. And that's most frustrating thing. Yeah, and but does not happen always. That sometimes that happens. Yeah.
Okay, thank you. Thanks for that. Connor, would you care to share your thoughts on pleasant and disappointing surprises in research?
Sure, and I think I'm going to echo what was said before me, but and especially as a synthetic chemist, things are surprising when you have a plan and it works out perfectly the first time, although that shouldn't be surprising, but it doesn't happen too often. And then the other side of that coin is you have a plan and it should work and it doesn't, and you can't figure out why. But of course, in hindsight, that's kind of science, right? You're always reevaluating your hypotheses. So that's perhaps the lesson there.
Okay, thank you, Connor. Jordan, you have any thoughts to share on this?
I would say to start with the disappointing part of it is as exciting as it is to share your research and gather feedback behind it. The frustrating part behind it that I came across with it was the whole IP process of it and making sure that that work stayed true and near to me and that it didn't go and gravitate towards either other companies or someone else running with the same idea. And then from the positive side of it, I would say that it has allowed multiple opportunities to come across that I wouldn't have explored myself when it comes to different positions. Like maybe, for example, something that was offered was like data analyst. Like that wasn't something I considered, but of course, with being a researcher, that is part of the field, and I do thoroughly enjoy it. So now that I enjoy it from a academic standpoint, I can now transition that into a career path and industry experience.
Great. Okay, thank you, Jordan. And Hannah?
Hello. So exciting part of my research is, well, previously before joining the lab at Temple, I was working with a different kind of data. So rather than whole genome sequencing, I was working with RNA-seq, and then it was cancer rather than like, not that my research has to be limited to viruses because it can be actually applied to all these different kinds of species. But like with 10 million sequences, like it was easy to sometimes apply to viruses. But yeah, so that was and I learned a lot in the process, and that was a pleasant surprise. Yeah, so, and it feels like, well, in my previous career, I did learn a lot about like medical side of things, and well, it was inspiring there as well, working with doctors. But here, it's a real-time thing, and I got a different kind of motivation. And I think I like my research. Yeah.
So you wouldn't change anything?
Nah. So that's the good part of it. The bad part of it is, well, okay, it's been 2 years, and it would have been nice to go to conferences and actually meet people and discuss research, and that hasn't been happening. I mean, I go to virtual conferences. Right. I mean, there are pros and cons, I guess. I mean, conferences are cheaper, definitely. Yeah. Yeah, that was a.
Yeah, that's a very good point. They're only just starting up again. The timing on that has been rough for all you guys. So it looks like our judges are still working. They're probably in having impassioned, vicious arguments with one another. Hopefully they come through this okay. In the meantime, I want to ask another question of each of you. If you were not going to be a scientist, what career path would you choose if you weren't a scientist? So let's go in a different order this time. I think we'll have how about Connor first, and why?
Oh, you picked the wrong person. I need time to think on this.
Oh,
No, it's okay.
okay.
In all honesty, I would probably, I mean, I suppose it's somewhat related, but I would probably go into education, be like a school teacher for like, you know, like public school, high school, middle school, something, and really focus on trying to be like a athletics coach.
Okay.
That would probably be me.
Okay. Great. Education and athletics. That was what my father did. So I can resonate with that answer. Ashley, how about you?
So I wanted to do science for a really long time. So I didn't spend a lot of time thinking alternatives. The non-science job that I've had that I enjoyed the most was like working in like the hotel sort of industry and planning people's vacations for them. And I feel like I could do that if I ever burn out completely. I can tell you where to take a trip and book you plans and reservations and things. Or a teacher, but you took that one, so we'll go hotel concierge.
You could be a travel agent and
I
advise
could.
people on where to go to find the most efficient watersheds in the world.
Absolutely. Yeah, we
Yeah.
could do ecotourism or something.
Yes, exactly. Wonderful. Okay, Hannah, how about you?
I think I would have become a writer. So I really like reading classical novels and all. Well, I like just writing. It's very soothing. And have you actually noticed that my title was actually like a parody of Hamlet? To be or not to be? That is the question. Yeah.
I did
So
notice
something like that. Yeah. So yeah, I think if I were not a scientist, I would have been a writer. And
Excellent. That's a great answer. How about Jordan?
It's kind of correlated, but I would definitely do something in the healthcare field. So um, maybe, I don't want to say pharmacist, but maybe something of like medicinal practices and of that nature, just because to me, that's where I gravitate towards outside of the whole science. And I think that with that, it allows for a constant need. And that way I know I have job security.
Right, right. Healthcare is much more than science. It's also there's the care part of it, right?
Right.
It
The
sounds like,
personal effect. Yeah.
yeah, yeah. Okay, and Jay.
So, yeah, if I wouldn't be a scientist, I think I will be a mathematics teacher because in my family, every person is like surrounded by the teachers. My father is teacher, uncle teacher, auntie teacher. Everyone is teachers, and I was grown up in that kind of environment, and I love teaching. Like I had been in teaching field in Nepal for 8 years after my high school. I did part-time teaching. And I love to teach mathematics because I wanted to play with equations and then that high school math, actually, that's so funny for me. Yeah.
Great answer. So we have a bunch of people who are teachers at heart. Okay, so seeing that that there's still no conclusion from the judges, this must be a very tight and contentious competition, which is understandable. So we'll just chat some more. So I'll ask each of you this. Can you think of if there was a defining moment or some other maybe smaller set of life experiences that inspired you to become a scientist? I know I can think of a few for me, but I'd be interested in knowing if you can identify something that occurred in your life or some small set of things that put you in this direction that you're now on. And I think this time we'll start with, why don't we start with Jordan this time?
I would say coming from a background with attending Fox School of Business as well and getting a degree in digital innovation marketing, that gravitated my skill set to incorporate the science of it to where it tackles user experience, the digital brand management, the buyer persona, and things of that nature to be able to build out the environment of the science and be able to emphasize that personalization for each end user. So I think that's what gravitated me towards the science behind it. And
Okay.
I don't want to say it's a limitation, but science is just more than just, I would say more than just the technical aspect of it. So I think a lot of people don't take that into account, and there's a lot more creativity behind it than what it's actually portrayed.
Yeah, that's for sure, because we don't know what all the answers are. So you're absolutely right. It takes a lot of creativity to do this job. Thank you for that. How about Jay? Was there a defining moment for you that made you want to be a scientist?
Yes, but it's a kind of little bit funny moment that happened in my school life. Like, my country has been in the civil war when I was in school life. It was 10 years of civil war. And one thing that happened is when I was returning from school to home, we had science practical classes, and we used to have electrical connection wire in my bag. And that civil war is happening around our district. And at that time, like, military was searching in the bag, and then that they found my electrical wire, and then they were cautious about that. They inquired me, and then I was very childish mind at that time. And later I realized that what happened with this kind of electrical connection, why they inquired me. And that that motivated me towards this field. Actually, that was very childish. I was in 8th grade when these things happened. Yeah. It's a little bit unusual.
That's great. Great. Thank you, Jay.
Mhm.
Hannah, how about you?
So I volunteered at a hospital when I was in high school. So it was I was in 1 week I was in a maternity ward, and the other week I was in the transplant section of the hospital. And it was a very different atmosphere, but I wanted to find ways to help these people get healthy. And well, becoming a medical doctor was, I didn't think I was going to be able to do that. And I decided to find a different path. And initially, well, yeah. So as I said before, I thought maybe working on pediatric cancer was one of the ways to maybe do it. But right now, infectious diseases, and given the urgency of given the urgency of SARS-CoV-2, and we are basically living now, gonna have the new normal, like living with COVID at this point. But yeah, I thought that was worthwhile. But anyways, yeah, the high school experience was the defining moment.
Okay, wonderful. Thank you. Ashley?
Well, I think what one made me want to go into sort of an environmental career was a day trip I took in middle school with the Chesapeake Bay Foundation. And we were jumping into this marsh mud, and it smelled like sulfur, and everyone was saying, "This is awful. Why are you in there?" And I was like, this is the best thing that I've ever done. Like, for some reason, this sulfur, like, decomposing plant marsh mud is the coolest thing I've ever seen. Like, I love that we're touching snails. I think it's super cool. And so I think that sort of like set me off in like, this is what I want to do with my life. I want to figure out a way that I can play in mud all day. And here I am.
Where earth and water mix is your first love.
Thing. It's all about mud.
And how about Connor?
So I've always sort of gravitated towards the, I guess, the tinkerer archetype, whether it be like, movies, cartoons. I think back to like the Ninja Turtles cartoon. I was a huge fan of Donatello, who was like the tinkerer of the group. But probably for me, like a coming of age moment, if you will, was I guess 7th grade. My science teacher recommended that I go to science camp, so I went, and it was like a clinical research setting. And we were just doing pipetting, but I thought it was really awesome. So I pursued that, and here I am.
Wonderful. Thank you, Connor. I think I want to check in and see. I think as I was hearing that the judges were nearing completion, I think I want to see if we have any resolution on that, or if I need to ask another question. Let's see. Are we ready? Okay, we are ready. The moment has arrived. Okay, so the awards for that we're going to be announcing here will be the first place prize is $500. Second place prize is $250, and the People's Choice Award is also $250. So I'm going to start with announcing the second place prize. Second place prize goes to Hannah Kim. Congratulations, Hannah. Next, I will award the People's Choice Prize. The People's Choice Prize goes to Ashley Kirker. Congratulations, Ashley. And now the moment you've all been waiting for, the first place prize by consensus of our judges goes to Ashley Kirker. Congratulations, Ashley. And congratulations, Hannah. And thank you so much. That was, I understand, a very contentious discussion between the judges. It seems that the People's Choice and the judges agreed on the first place, and the others were very, very close. All of these were really excellent presentations. And I want to say thank you to all of the participants, as well as to the judges. So thank you so much for taking the time to prepare one of these. I know it is difficult to prepare a 3-minute talk on a 5 or longer year degree. So thank you to all of you for taking the time to do this. Thank you for the judges for taking the time out to participate, and for your service to the college and to this Temple community. And thank you also to the College of Science and Technology Graduate Affairs, especially to Megan, who organized all of this and put this together. Megan doesn't tend to show her face here. She's very humble, but she's behind the scenes and she's making all of this happen. So thank you to Megan. And thanks to all of you participating, and hope to see you all next year. And congratulations, everyone.
Thank you.
Thank you. Bye.
Thank you, and
Bye-bye.
congrats.
Thank you. Bye. Thank you.